Hello everyone, it is my great honor to be here to share our work with you. My presentation will include 3 parts: a brief introduction about mobile edge computing, a brief introduction about deep learning, and our work, as well as some contributions. According to the survey, in 2019, the number of mobile internet devices is over 6 billion. As we can see from this slide, there is a great growth in recent years from 2010 to 2019. Meanwhile, the wireless network is facing a number of challenges. Due to the physical size constraint, mobile devices are in general resource constrained and high energy consumption. We can see from this slide, there are significantly increasing power requirements in the network. Also, there are many systems have high real-time requirements, such as vehicle communications. Therefore, mobile edge computing is envisioned as a promising approach to address such a challenge. Different from cloud computing, mobile edge computing can upload data to the nearby servers to elevate the task computing. However, a good algorithm with low time complexity for task offloading is required. Why do we use deep learning in this paper? Deep learning is famous for its good performance in computer vision, vehicle detection, and face recognition, and so on. In 2020, Baidu company provides driverless taxi in many cities, and it proved that the deep learning has good performance in computer vision. As neurons in deep learning can represent the complex image problem, even a life problem. Before this, I would like to introduce our works in this paper. In our paper, we model a small communication network, which is consisted of multi-user with multiple tasks, and one access point, and one server. To jointly optimize energy consumption and time cost, factors including task size and channel state information, as well as bandwidth, are considered. The optimization problem is formulated as problem J. It is constrained by bandwidth C, and we use X denotes the offloading decision. If the task is executed by local devices, we let X equal to 0. Otherwise, if the X is executed by edge server, X is equal to 1. In the problem J, we use EL denotes the energy cost of task for local processing, and ER denotes total energy cost of task for edge processing. Also, TL denotes time cost of task for local processing, and TR is total time cost of task for edge processing. To simplify the problem J, we firstly fix the bandwidth allocation by using the strategy, which is based on task size and channel state information. Once the bandwidth allocation is set, the problem J will be simplified into the J star. So, given the simplified problem, how can we solve it with deep learning? Does it perform better than other algorithms? As the slide shows, the right picture is the traditional supervised network architecture. Input data size and channel state information. With neurons computation, we make corresponding offloading decisions. But there are some advantages. If we use traditional supervised networks to solve the problem J star. Firstly, it is hard to get correct labels and date. Even worse, only one network can't solve the problem well. That's to say, we may get bad offloading decisions. So, based on it, we propose a distributed unsupervised learning network. As this slide shows, input data size, channel state information. We can get a better decision among these networks. These networks are the same architecture. They have the same input layers, hidden layers, and output layers, but they got a different learning ability. With given decisions, we will store tasks and decisions as key value pairs into the memory pool. And by updating the memory pool, we can get correct labels to train the neural networks. And with thousands of iterations, we can get good offloading decisions. Details about neural computation is shown as this slide. K-1 and N is the output of the last layer, and secant NM is the corresponding weight between neurons, between N's and M neurons, and the BKM is the corresponding weight, which is hidden. Also, in hidden layers, we employ ReLU active function like this. And different from ReLU active function, the output active function is given by this formula, which is the output value is 1 or 0. Next, there are some results about our work. We analyzed 4 schemes. Results are shown at this slide. Local cost doesn't change with ES, since the ES is the energy consumption per bit of data processed by server, and grid cost is the emulation strategy, and we can get the minimum cost. We can learn from this slide. The proposed algorithm can save 14% cost than local schemes, and it can also save 18% cost than edge schemes. To test whether the algorithm can meet the real-time requirement of the system, time course with different number of networks is tested. We can learn from this slide. When channel state is considered, it costs 0.02 seconds more than the ideal communications. Since there are more data to compute, and when the number of networks is less than 6, the proposed algorithm generates near optimal solution in 0.2 seconds, especially when the number of networks is 2. We can get a solution within 0.1 seconds. Also, we use testing samples as input layers to analyze the robustness. As this slide shows, the trained model can generate a near optimal solution over the gain ratio 0.95, even with different hyperparameters. The gain ratio meaning is the gap between decision cost and the minimal cost. In this paper, a multi-user with multiple test scenario is considered. Taking full account of factors including data size, channel state information, and bandwidth, we propose a supervised learning-based offloading algorithm for test offloading. In this network, we use distributed parallel networks to guarantee the robustness. Additionally, we import a memory pool to store input data and corresponding decision as key value pairs. By exploring the advantage of deep learning and parallel architecture, the algorithm makes up for the disadvantage of traditional algorithms, such as decision delay. Compared with supervised learning, It avoids the complex work of data separation and has better robustness. And numerous results show that the proposed algorithm can achieve near-optimal decision, timely as well as high reliability. That's all. Thank you.
Hello everyone, my name is Zhihao Xun from the School of Computer and Information Engineering, Zhejiang Gongshang University. It is a great honor to introduce my paper here. The title of my paper is Decoupling, Offloading Decision, and Resource Allocation via Deep Reinforcement Learning and Sequential Least Squares Programming. This introduction will be divided into the following 5 parts. They are Introduction, System Model, Authorities, Performance Analysis, and Conclusion. The first part is the introduction. Edge computing is a distributed computing framework that brings enterprise applications closer to data source, such as IoT devices or local edge servers. This proximity to data at its source can deliver strong business benefits, faster insights, improved response times, and better bandwidth availability. In the past, the promise of cloud and AI was to automate and speed innovation by driving actionable insights from data. But the unprecedented scale and complexity of data that's created by connected devices has outpaced network and infrastructure capacities. Sending all that device-generated data to a centralized data center or to be the cloud cases bandwidth and latency issues. Edge computing offers a more efficient alternative. Data is processed and analyzed closer to the point where it's created. Because data does not transfer over a network to a cloud or data center to be processed. Latency is significantly reduced. Edge computing and mobile edge computing on 5G networks enables faster and more comprehensive data analysis, creating the opportunity for deeper insights, faster response times, and improved customer experiences. Since there are a large number of terminals accessing the MEC system in practical applications, how to ensure that the MEC system can provide services stably to the outside world in the huge computing offloading. Each server also usually has limited computing resources, so the offloading and the resource allocation problem have become key issues in edge computing. Next, I will introduce the system model. The structure of the edge computing system in this paper is shown in the figure, which includes an edge computing server and end-user equipment. The edge server and the user equipment are connected through a wireless network. The transmission delay between ES and UE is very small and can be ignored. As just said, ES has limited computing resources. Therefore, ES needs to determine which UEs offloading their tasks to the edge server and allocate computing resources. As mentioned earlier, the user device has two options, namely local computing and offloading. Now I will introduce the different cost functions corresponding to those two choices in the system. First, the task offloading. Set the data volume of the task as D and the upload speed of the user's device and the computing speed of each service as R and F respectively. Then the time required for UE to perform task offloading is D divided by R plus D divided by F. We also take energy consumption as a part of the cost function. Assuming that the power of the user's device when transmitting data and waiting for the results are P upload and P waiting respectively, the total energy consumed by UE when selecting task offloading is P upload times T upload plus P waiting times T waiting. Next, the local computing. Similar to what was said earlier, under this option, UE consumes time of D divided by F and energy of P times T. In order to minimize the delay and energy consumption of all user equipment, this paper uses a linear weighting method to define a weighted function where alpha represents the ratio of delay and energy consumption in the cost function. Now our task is to make the offloading decision X and the resource allocation R according to the amount of data calculated by user's device, so as to minimize the cost function. The next section is an introduction to the orthography. The process of the orthography proposed in this paper is shown in the figure. The orthography is based on deep reinforced learning and sequential least squares programming. It can learn without pair training and adjust its strategy dynamically according to the change of the environment. Firstly, the data D is input into the neural network. The neural network will generate an offloading decision based on D. Because the neural network is not trained in advance, the offloading decision will not meet our goal. So we randomly perturb it to generate k different offloading decisions. According to those k decisions, k resource allocation schemes are generated. Next, according to those k schemes, the corresponding cost of each scheme is calculated, and the scheme with lowest cost is selected for output. The output scheme and the input D will be added to the memory part. After each prediction produces a fixed number of offloading decisions, the neural network will randomly select a bunch of symbols from the memory section for training, so as to improve the generation of uploading decisions. For the above neural network, we use a neural network with 4 layers, which has a good classification effort. The training rate is 0,1 and the training interval is 10. The size of the 2 hidden layers are 120 and 80 respectively. For the resource allocation authority, we use an authority called Sequential least squares program. It can be used to solve nonlinear programming problems that minimize a scalar function. Here is the performance analysis section. The 2 figures are the training loss of the neural network and the ratio of the minimal cost in the iterations to the concurrent cost, respectively. It can be seen from the left figure. When the number of iterations reaches about 4,500, the loss basically stabilizes, and the rate of decline slows down significantly. When it reaches about 6,500, it basically no longer declines, maintained between 0,1 and 0,2. The ratio in the right is recorded every 10 iterations. The blue line represents the average ratio of the nearly 20 records, and the blue shading represents the maximum and minimum values of the nearly 20 records. You can see from the figure that it can be seen that after 4,000 iterations, the ratio basically stabilizes, changing around 0.995. Now the 2 figures are respectively the training loss and the ratio of minimal cost in the iterations to the concurrent cost when alpha changes. In particular, when the number of iterations is 5,000, alpha will become 3, and when the number of iterations is 7,000, alpha will change back to 1. It can be found that the training loss in left figure has increased significantly at 5,000 and 7,000 times, and then quickly converged, while the ratio in the right figure is the same. There has been a significant decline, and both are resumed after about 1,000 iterations. Now the 2 figures are respectively the training loss and the ratio of the minimal cost in the iterations to the concurrent cost when shutting down and turning on 3 user devices when the number of iterations is 5,000 and 7,000. It can be seen that the impact of switching on and off the user equipment is less than the impact of change on alpha. After a small increase in loss and a small decrease in cost ratio, it quickly returns to the previous level. It can be seen from the above two experiments that the model can quickly adapt to changes in the environment. Now we compare the proposed authorities with the following strategies, which are all local. All user devices calculate tasks locally. All offload. All user devices offload tasks to the edge computing for calculation, and all user devices are equally offloaded. CD average, the offloading strategy is calculated by the gradient descent method, and the offloading resources are equally divided among all user devices. CDSLSQP, the offloading strategy, is calculated by the gradient descent method, and the computing resources are allocated using the SLSQP authority. It can be seen from the figure that all local offload and CD average perform poorly, and the ratio of the minimal cost to the concurrent strategy cost is between 0.9 and 0.84, and the CDSLSQP authority performs best, with the cost ratio close to 1, which is stable at around 0.998, and the authority proposed in this paper after a period of convergence. The cost ratio stabilizes at around 0.995. It can be seen from the table that the time consumed by the authority proposed in this paper to generate an offloading strategy and the resource allocation plan is much smaller than that of CDSLSQP authority, and the time consumed will increase greatly when the number of user equipments increases. In this paper, a computational offloading decision and resource allocation authority based on deep reinforcement learning and convex optimization is proposed to solve a highly coupled problem. The results show that the proposed authority has good performance and less time consumption. We also think that the method has good extensibility, and we can easily use this authority to solve other similar problems. Thanks for your attention.
Hello everyone. Today I will introduce my research to you. It's about gradient-based fast intro prediction algorithm, or VVC. The main contents include the following four parts. With the rapid development of video technology, people have higher requirements for the video experience brought by video. High-definition and ultra-high-definition videos have drawn more attention, since they can return more abundant image details and provide more realistic video effects. However, the network transmission of HD and UHD videos is faced with a great challenge due to the huge data volume brought by HD and UHD videos. With high resolution and extensive range of luminance. Therefore, JVET have launched an emerging video coding standard, namely Versatile Video Coding, or VVC. VVC still adapts the hybrid coding structure in HEVC. The 7 function modules included in VVC coding framework are intro prediction, motion estimation, and motion composition, transfer and quantization, entropy encoding, inverse quantization and inverse transfer, in-loop filter, decoder picture buffer. In order to better adapt to the local texture features of the image, VVC employs QT&T as partition structure. The partition process of coding tree unit is as follows. The coding tree unit is partitioned by quantity at first. Then, the NIF nodes in the previous step can be further partitioned by quantity or multi-tap tree until the maximum partition depth is reached. As illustrated by this figure, QT&T includes quantity and multi-tap tree, which consists of vertical binary splitting, horizontal binary splitting, vertical ternary splitting, and horizontal ternary splitting. VVC adopts 37 intro prediction modes in coding unit, as shown in this figure. The 65 directional prediction modes, or VVC, have the same direction range as the 33 directional modes of HEVC, but the granularity is smaller. When selecting the best intro prediction mode of the coding unit, it's necessary to traverse these 65 modes and select the one with least RD cost. In order to simplify the intro prediction process of VVC, the classical 3-stage fast intro mode scene is adopted. Firstly, M modes with the least edge cost is selected through rough modes scene. Edge cost is calculated by equation 1. DSATD is the sum of absolute transfer difference of residual signal, which represents the distortion of the current prediction mode. Lambda is the Lagrangian multiple, and bit mode represents the number of bits that is required for encoding in the intro prediction mode. Secondly, most problem modes are taken into account to update the candidate list. Thirdly, 2 or 3 modes with less cost are involved in the weight distortion optimization process. To select the least RD cost mode, which is the optimal mode for coding unit. The RD cost is calculated by equation 2, where the SSE is the sum of the circled arrows between original coding unit and the reconstructed coding unit. Then I'm going to introduce our algorithm. In order to reduce the computational burden of encoder through reducing the number of partition patterns that need to be traversed encoding unit, we explore the new partition types distribution in VVC test model 7, which can be called VTM7 for short. We count the QTMT distribution information of 6 video sequences with different resolutions, motion characteristics, and contents. From Table 1, we can observe that the probability that the empty partition is selected is high. In addition, the ranges with relative complex texture are more likely to be partitioned by empty to achieve better prediction results. We find an approach to speed up the coding process, that is to skip some partition types according to the gradient of coding unit. We use the Sobel operator to extract the gradient information. Gxij and Gyij represents the gradients of each pixel in horizontal and vertical direction respectively. Mij represents a 3x3 matrix centered on the pixel with coordinates ij, gx, and gy are the two convolution masks of Sobel operator. Equation 5 and 6 are the calculation formula of the absolute total gradient of coding unit in horizontal direction, namely gx total, and the vertical direction, namely gy total, respectively. We add the absolute gradients of the coding unit in horizontal and vertical direction to get the absolute total gradient of the coding unit, namely G total, as equation 7. Fast stereo partition design is as described as follows. If G total of the coding unit is greater than TH and GX total is greater than GY total, then classify the coding unit to horizontal texture CU and skip vertical binary splitting and vertical ternary splitting. If G total of the coding unit is greater than TH and GY total is greater than GX total, then classify the coding unit to vertical texture CU and skip horizontal binary splitting and horizontal ternary splitting. Otherwise, classify the coding unit to other CU and traverse all partition types. The threshold in this section is important to select the coding units with larger size or richer texture, which are highly to be further partitioned. BDBR represents a percentage of the code rate that can be saved by a certain encoding method under the same objective quantity. TS represents the coding time saving. We explore the relationship of BDBR, TS, and alpha. We find the BDBR and TS decrease with alpha, and there exists a corner point for curve of BDBR, from which the curve starts to be steady. Therefore, this point can be selected as the value of alpha. Alpha is set to 700 in this work. In VVC intro prediction, the most time-consuming part is the calculation of RD cost. Although VVC introduces three-stage fast intro mode design, the coding complexity of VVC intro prediction is still very high. Therefore, we propose a fast intro prediction mode saying algorithm according to the gradient information in order to analyze the correlation between the best intro prediction mode and gradient information of coding unit. 6 sequences are tested. Set 1 means the situation that the coding unit is classified to horizontal texture CU, and the distribution of the best intro prediction mode is between 2 to 33. Set 2 means the situation that the coding unit is classified to vertical texture CU, and the distribution of the best intro prediction mode is between 34 to 65. Set 3 means the situation that the coding unit is classified to horizontal texture CU, and the distribution of the best intro prediction mode is between 34 to 65. Set 4 means the situation that the coding unit is classified to vertical texture CU, and the distribution of best intro prediction mode is between 2 to 33. Set 5 means the situation that best prediction mode is planar mode or DC mode. From Table 2, we can find that DC mode, planar mode, and the mode conform to the measure age of image would probably be the best prediction mode. However, some unexpected situations should not be ignored. We propose a fast intro prediction mode saying algorithm. At the first stage of rough mode saying, if G total of the coding unit is greater than TH, and the GX total is greater than GY total, then skip the mode 36, 40, 44, 48, 52, 56, 60, 64. If the G total of the coding unit is greater than TH, and the GY total is greater than GX total, then skip the mode 4, 8, 12, 16, 20, 24, 28, 32. Overall algorithm is described as this. Next, we go to present the simulation results. This fast intro prediction mode algorithm was implemented in VTM7 reference software. On the condition of all intro, 30 frames of each sequence of all classes are tested with QP value of 22, 27, 32, and 37. This table represents the results of the proposed algorithm compared with VTM7. From this table, we conclude that the proposed algorithm compared with VTM7 can save 47.78% of the encoding time, with 2.25% BDVR increase and 0.09 dB BDPSNR decrease. Here display the partition of the first frame from basketball drive sequence by using the default algorithm in VTM7 and the proposed algorithm separately. For some areas with flat texture, the partition results of the two algorithms are the same, but for areas with more complex texture, the two algorithms are partitioned in different ways. Although the proposed algorithm skips some partition in areas with complex textures, resulting in a difference from the partition result of the default algorithm in VTM7, The performance degradation caused by this difference is almost negligible. Two decoded frames from daylight road sequence by using different algorithms are displayed. The naked eye can hardly identify the difference between the two frames in this figure. There is almost no difference between these buildings and vehicles. The main works are summarized. A fast serial partition algorithm based on gradient has been proposed. A fast mode scene algorithm by skipping some modes has been proposed. Combining the two algorithms can effectively reduce coding time. The algorithm proposed in this paper can be applied to scene theories that require high real-time video transmission, such as live broadcast and video communication. That's all. Thanks.
Hello everyone, my name is Song Shaojie. I'm studying as a second grade postgraduate in Guilin University of Electronic Science and Technology. The subject of today's presentation is performance analysis of multipath mitigation using different anti-multipath techniques in BPSK and BOC modulated signals. Now, today's lecture is divided into 5 parts, namely introduction, related work, using method, the experiments and results, and the conclusions. Now let's look at the first part, introduction. The introduction introduces the cause of multipath effect and its influence on the received signal, taking BPSK and BOC signals as examples, several specific multipath mitigation techniques as presentation. BOC signals has a narrow auto-correlation peak with than BPSK with the same anti-path method, as can be seen from the figure 1. The figure 1 shows the comparison of the auto-correlation function of the BOC and the BPSK signal. However, due to the multipath peak of the correlation function, the error log point appears in the phase identification curve and the multipath inhabitation performance is greatly reduced. In order to solve these problems, a gating signal correlator method was introduced to suppress BOC signals multipath effect. Let's look at the second part, the related work. The second part focuses on the preliminary work done to solve the problems in the introduction. These include giving general expressions for BPSK and BOC and expressions for receiving signals in the presence of multipath signal influence. Based on this, a basic mathematical model for analyzing multipath problems is constructed. We can see slide. We can see the BPSK receiver received the superimposed signal of the satellite direct signal and the multipath signal reflected by the objects around the receiver. So, the BPSK intermediate frequency signal received by the receiver can be expressed as ST. The BPSK immediately frequency signal received by receiver can be expressed as ST. In the presence of multipath signal, the received signal can be expressed as a superposition of the direct signal and the multipath signal. Let's look at the third part. The third part introduced two multipath suppression methods. Narrow correlation method and the gating signal correlator. Narrow correlator technique is widely used in navigation receivers as the earlier effective multipath mitigation technique. It improves the anti-multipath compatibility of the code tracking ring tracking loop by reducing the space between early character and late correlator, using the correlation function early and late. The method discrimination function can be denoted as earlier minus later. Fingers 2 shows the phase discriminator output of BPSK signal and BOC signal where a narrow character interval D is link 0.1 TC. The other method is gating signal correlator method. The gating signal correlator method is a signal correlation calculation method similar to the narrow correlator. The locally generated code of the gating signal correlator method is no longer the recurring code generated by a traditional receiver, but one or more gate-like signals called gating signals. We can see from the finger 3, it shows the gating signal corresponding to BPSK and the signal BOC EE. In the finger 3, the gating signal waves corresponding to BPSK and the BOC signals are given. It can be seen that the gating signal is a bipolar non-zero code, and all of them are at the edge of the signal chip. Okay, let's look at the first part. The first part is experiments and results. One is the BPSK signal and the BOC signal using narrow correlator technique are simulated and analysis in terms of multipath error. The simulation results are shown in finger 4 and finger 5. As we can see from the finger 4 and 5, the narrow correlator technique has significant effect on BPSK and the BOC signal multipath mitigation. With a smaller correlator interval, the better the multipath mitigation effect is. There are no other false log points. However, it's different for BOC signal. Since the main peak of the autocorrelation function of the BOC signal is sharper than the C code, its multipath mitigation effect is better relative. Now look at the next experiments as gating signal correlator for BPSK and BOC. Now the following figures show the block diagram of code tracking loop when the received signal is processed by the gating signal method. Is this. The BPSK signal and BOC signal using gating signal correlator technique are simulated and analyzed in terms of multipath error. The simulation results are shown in finger 7 and finger 8. Finger 7 and 8 is a gating signal. The gating signal has the same period as the CA code. The influence of the CA code is considered, so the waveform of the gating signal corresponding to the phase inversion position of the CA code, the cross correlation function of the gating signal, and the input signal is directly used as the phase discrimination function. The phase discrimination curve is shown, and its multipath error envelope curve is shown in figure 7b and figure 8b. It can be seen from the error envelope curve. The smaller the duty ratio of the gating signal, the smaller the multipath error. Okay, the first part is over. The next part is conclusions. As a new type of navigation signal, BPSK has many advantages such as sharper man peak and high ranging accuracy. It can be seen from the figure 1. The correlation of autocorrelation function of the BPSK signal. The man peak is sharper than BPSK for BPSK. However, multipath error is still one of its main sources of error. In this paper or in this presentation, the multipath mitigation effect of BPSK and BPSK signals using narrow correlation method is analyzed and compared. The study shows that the BPSK narrow correlator phase discrimination function has phase discrimination ambiguity. The BPSK signal must be accurately captured and tracked in order to have a good multipath mitigation effect. According to the theoretical formula derivation and simulation, a gating signal correlator and the narrow correlator method have the same effect on multipath mitigation. When the correlation, we can see it from the figure 8, figure 7, and figure 5 and figure 4. When the correlation function of the gating signal can be used as the phase discrimination function of the code tracking loop of the BPSK signal, there is no problem of phase discrimination ambiguity. However, the correlation function of the gating signal as a phase discrimination function of the code tracking loop of the BPSK signal has the problem of ambiguity. This problem we can reference the above figure 5. We can see this discrimination function curve exists the node 0 false pouch look. Therefore, when the traditional narrow correlator and gating signal correlator methods are used for multipath mitigation of BPSK signals, measures must be taken to ensure that the signals are used under the premise of character acquisition and tracking. Okay, that's all. That's all for this presentation. Thank you very much for listening my presentation. Your valuable comments are also welcome. Thanks again.
Hello, ladies and gentlemen. My name is Luo Shangwei. I'm honored to be here to share my work, which is my paper, Application of EQSys and TOPSIS method in the evaluation of integrated equipment system or systems. I'm going to talk about 5 aspects, and you can see in this table of contents. The first is the background of the paper. The second is the main problems at hand. The third is the main work. The fourth is the analysis of results. And finally, the conclusions reached in this paper. As you may know, with the development of information technology, the battle between individual soldiers can no longer meet the concrete combat environment and ushered in the confrontation between the system of systems. And showing the figure, naval base, sea, and air coordinated attack, sea defense, and other different combat systems in one joint operation. IS is a heterogeneous weaponry system coupled upward from different functional nodes and subsystems in accordance with the overall requirements of building an information-based army and winning an information or war. Assessing the operation effectiveness of IS in a reasonable and effective, which can play an indispensable part in optimizing the system structure and accelerating the development of weaponry. It can be able to fight and win the war security. Therefore, it is particularly important to find a responsible and effective algorithm to evaluate the contribution of the equipment body in the integrated equipment system. You can see in the picture. which tell us the main problems at hand. The current algorithm mainly uses the number of ODA loops and the expert evaluation information to judge. The traditional evaluation algorithm does not consider the ambiguity of the expert judgment information, the unconsult of the weapon and equipment body itself, and the equipment body combat may cause malfunctions. Therefore, it leads to inaccurate effectiveness evaluation of equipment systems. The research conducted in this paper is based on the above questions. So, I start my work. Next, you will know some of the work I do. First, we model the structure of IS and showing the figure. IS presents a train-like hierarchical structure from top to bottom, composed of functionally interconnected and performance complementary equipment weapons. Secondly, I established the system of combat capability indicators and showing the figure. The capability indicator system in this paper consists of 3-level capability indicators, namely detection capability, decisive capability, and attack capability. When evaluating the contribution of equipment in the IS, the characteristics of the IS should be considered. Moreover, the contribution of equipment naval weapons should be calculated through expert evaluation information. As shown in the figure, this paper combines entropy weighting method, the Gini coefficient method, and AHP to calculate the weights of combat capability indicators. Considering the uncertainty of expert evaluation information, thus the relative proximity is obtained by the value set and TOPSIS method. Finally, the joint weaponry linear function collaboratively evaluates the contribution of the weaponry. In this study, linear weighting will be used to obtain the weights of the combat capability indicators. The use of linear weighting can easily express the subject weight and objective weight of the expert evaluation information. Moreover, this can ensure the accuracy of the combat capability indicators. Operational indicator weighting values are obtained by linear weighting of entropy weighting method, the Gini coefficient method, and AHP. Immediately following the use of VQ and TOPSIS to evaluate the contribution of integrated equipment systems. It consists of the following 6 main steps. Step 1. Converting evaluation information into the VQ value. Step 2. Constructing the VQ decision matrix. Step 3. Identification of the idle vapours. Step 4. Combined VQ and TOPSIS calculations to assess the distance to best case solution and worst case solution of the vapor queue. Step 5. Calculating the close degree of proximity of vapor. Step 6. Ranking the close degree of proximity of vapor. Then, in this paper, IS force are divided into new and recurrent force, and the probability density functions of new force and recurrent force are derived quantitatively by formulas. The field algorithm from assessing the contribution of the vapor system is obtained and showing the formula. Part 4 is case analysis. Judgment matrix B and decision matrix C divide from the expert's evaluation of equipment to be assessed, and they will be used as input sources. It is valid to obtain the combat indicator weights by linear weighting, and showing the figure. It's unreasonable to obtain the weighting of the combat capability indicator by AHP. Ignoring the objectivity of the evaluation information, linear weighting finds a balance between subjectivity and objectivity. The simulation group shows that the linear weightings are always between subjectivity and objectivity. This can prove linear weighting. Consider both subjectivity and objectivity. And showing the figure. When the number of failures is constant, the contribution of the vapor to the overall changes with the change of the beta value. When beta equals 0, S1 has the best effect, and the beta value rise. The impact of cost becomes smaller and smaller, and more attention is paid to the degree of vapor completing the mission. When beta equals 1, it is equivalent not considering the influence caused by the number of failures. It is only related to the closeness of vapory, which is consistent with the close degree of proximity of vapory. Normalized results in the table. And the closeness coefficients of vapour S1 and S2 are relatively low. With the increase of beta value, the impact of cost becomes weaker and weaker. Its contribution to the entire system is also lower and lower, and the curve shows an downward trend. On the contrary, S3 and S4 show an upward trend. The last part is the conclusion. From the above analysis, it can be concluded that this paper considers the contribution of IAS using a compilation of WIGU and TOPSIS when considering equipment failures. It provides new ideas from evaluating IAS. Moreover, simulation shows that the algorithm in this paper can be used to find the balance point between loss cost and combat capability, and provided the theoretical basis from decision makers to select suitable weapons and equipment and accelerate equipment development. That's all. Thanks for your watching and guidance.
Hello everyone, my name is Yu Siyuan, and I'm now a third-year master degree student in Tongji University. Today, I'm going to share my paper, A Transmission Design via Reinforcement Learning for Delay-Aware V2V Communications. I will introduce my paper from 5 parts. First, I will give a brief introduction. Then, I will describe the system model and MDP formulation in detail. After that, I will show the performance of my method. In the end, I will make a conclusion. So now, let's start from the introduction. In recent years, several issues occur in the modern transportation system, such as traffic congestion, energy shortage, and road safety. Supported by the great progress made in the Internet of Things and other advanced technology, intelligent transportation system has been widely accepted as the promising solution. As one of the key ITS technologies, Internet of Vehicles enables information to be shared among vehicles, so that various ITS services can be developed. However, such applications are in general safety related and always have strength delay and reliability requirements. Realizing high-quality communication is challenging. In Internet of Vehicles, diverse services can be conducted, such as entertainment services, warning services, and environment sensing services. These services always has different quality of service requirements. Thus, it's quite necessary to proceed transmission design. The conventional designing procedure is mainly based on channel state information in the physical layer. However, CSI doesn't reflect time that source messages have already waited before the transmission opportunities are available. This may cause unbounded transmission delay. Involving the queue state information in the MAC layer into the decision-making process is essential. Our earlier work investigates a multi-user V2V communication network. In the network, each information source desires to send two-type delay-limited messages with different characteristics, and we solve the problem by Lyapunov optimization. However, the solution is established based on the instantaneous channel state information, which is almost impossible to obtain in IOV. Since reinforcement learning can solve a wide range of challenging sequential optimization problems, even without the environment knowledge, it quite fits our problem. Reinforcement learning is a kind of trial and error learning method. The decision maker is named as agent, and the agent can interact with environment. At the beginning, the environment gives a state ST and revert RT to the agent. Then, agent makes one decision. We call it action in RL. After the environment senses the action, with transition probability P, it will give a new state ST plus 1 and revert RT plus 1 to the agent. And with transition probability 1 minus P, it will give another new state ST plus 1 prime and revert RT plus 1 prime to the agent. Then repeat in this way until the agent finds a stable action to solve the problem. With RL, we can solve problems in many fields, including AlphaStar and AlphaGo, which play games excellently, and self-driving cars, finance, and so on. In my work, DQN algorithm is applied. It is a model-free reinforcement learning method that combines the Q-learning algorithm with deep neural network. Q-learning is a tabular of policy algorithm. Each element in the Q table represents the value of an action value function. The issue with conventional Q-learning is that when the state space or action space are large, the storage and update of Q table demand large memory space and long convergence time in the training process. DQN targets this problem by applying deep neural networks to approximate the action value functions. Now I will explain the system model in detail. As shown in the figure, a typical V2V communication scenario is considered. The source S desires to send messages to destination D. The operations of the whole system are conducted in multiple time division transmission blocks that consists of T unit time slots. At the beginning of each time slot, S executes transmission. At the end of the slot, D provides certain feedback to update the knowledge of S. The messages include two types. They have very different characteristics and QoS requirements. The first type messages, termed type 1 messages, arrive in S periodically with a fixed data rate R bit each slot. An example of such messages is the heartbeat messages, which can provide D with the real-time status of S in the warning system. For each transmission block, a sufficient proportion of Type 1 messages are expected to successfully reach D. The second type of messages, termed Type 2 messages, arrive in S randomly. The arrival date volume at time slot T follows a stationary random process. An example of these messages is the environment sensing data collected from the source onboard sensors. Sharing them with D can help extend the environment perception capability of D. These messages can be temporarily stored in the source queue, but the queuing delay must be limited. The message transmissions are conducted in a narrowband block fading environment. The fading coefficient between S and D at time slot T is denoted by HT, which remains fixed in each time slot but changes across different slots. To simplify the problem, we assume that the channel gain can be discretized into L different levels. The transition between each level can be modeled as a Markov transition process as shown in the figure. We consider a stationary environment such that the channel transition probabilities remain fixed, but are unknown at both the source and the destination. Due to the mobility of the vehicles, the source has only a delayed channel knowledge. At the beginning of any time slot T, S selects a read level from set M and a power level from set P to send the unit power signal xt. As a result, at time slot T, the received signal at D can be expressed as follows. Further, the source S can choose whether encoding only one type of messages or both types, and the transmission rate of each type message will be determined. If RT is greater or equal to R, then S has two choices. If the chosen data rate RT is less than R, there is only one choice. All the RT bits are used to transmit the Type 2 message. Moreover, the mutual information between S and D can be calculated. Due to the imperfect transmit channel state information, the transmission of xt may fail. If RT is less or equal to the mutual information, the destination D can correctly recover the message. Otherwise, correct decoding is impossible. From above, we define energy efficiency as the ratio of some effective data rate to some power consumption, and aim to find a maximized energy-efficient transmission strategy. The source can choose its encoding action, transmission power, and rate based on its queue state and delayed channel knowledge to satisfy the desired message delivery requirements in each transmission block. To solve the energy-efficient transmission design problem for the considered delay-aware V2V communications, we first define a finite episodic MDP that reflects the optimization problem. The state space is defined as follows, and each state consists of 4 items to respectively reflect the reliability state of Type 1 message, queue state of type 2 message, channel state, and the transmission block state. In addition, an abnormal terminal state is defined if the queue requirement or the reliability requirement is against. If the agent enters into the abnormal state, the transmission block ends immediately. As to the action space, each action in the space consists of 4 items, which indicates that the source can choose the power level, data rate, and the encoding state of 2 type messages. As mentioned before, the encoding state of 2 type messages are relative with the data rate chosen by the source. The reverse reflects how good the chosen actions are in terms of achieving the optimization objective while guaranteeing the constraints. It is the basis for the agent to learn a good policy. To this end, we form the reward by 4 parts: energy efficiency reward, reliability reward of type 1 messages, latency reward of type 2 messages, and penalty for entering the abnormal terminal state. The total reward of our MDP at time slot t is in a format of weighted sum. We can tune these parameters to specify our preference in maximizing the achievable energy efficiency, maximizing successful transmission ratio of the type 1 messages, or minimizing the queue length at the end of each transmission block. Next, I will show the performance evaluation. This is the DQN structure and the simulation parameter. And this is the learning curve. The training of our algorithm is conducted using mammalian episodes. We randomly select 6 possible states. For each update of the DNN weights, these 6 states are input to the network, and each generates 35 outputs corresponding to 35 actions. The average of the outputs are displayed in the figure. From the figure, it can be seen that our algorithm successfully converges. In the following, we discuss the results obtained from the 100,000 test blocks. We compare our DQN scheme with 4 baseline methods. The first follows the Lyapunov optimization scheme. Instantaneous channel state information at the source is assumed to be available. The other 3 approaches don't assume accurate channel state information. The second is the fixed rate scheme that always transmits with fixed rate using the smallest power level according to the delayed channel knowledge. The empty queue scheme targets addressing the above issue by always trying to empty the source queue. The worst-case scenario scheme works similarly to the EQ scheme, but chooses its power level according to the smallest channel gain that has non-zero transfer probability from the observed value. The left figure shows the average achievable energy efficiency of the 5 schemes with 3 different sets of quality of service requirements. The numbers of successful transmission blocks are displayed in the right figure. It can be seen that the proposed DQN scheme obtains much better performance than the WS scheme. Even though the RFR scheme and EQ scheme may attain higher energy efficiency, but both approaches lead to violation of the transmission requirements. Moreover, even though only delayed channel knowledge is available, the performance of the DQN scheme is comparable to the LO scheme. In the end, I will make a conclusion. In this paper, we have applied DQN in cross-layer transmission design, a typical scenario in which multi-types of messages with different quality of service requirements are transmitted with imperfect transmitter-side channel knowledge has been considered. We have shown that by transforming an energy efficiency maximization problem to a finite MDP. We can solve it efficiently through advanced reinforcement learning techniques. The simulation shows that our method is comparable to Lyapunov optimization method and performs much better than several heuristic solutions. So that's all. Thank you.
Hello everyone, I'm honored to have a chance to give the presentation on this special occasion. My name is Han Zhang, and I come from the State K Laboratory of Integrated Service Networks of Xidian University in China. The topic of my paper is research on construction of measurement matrix based on Welch bond. I will introduce my paper from 4 aspects: introduction, proposed method, perform analysis, numerical results, and conclusions. First of all, I will give you a brief introduction to compressive sensing, CS. CS is an innovative framework for data acquisition and reconstruction, which uses the sparse structure of most signals typically in the time or transform domain to break through the limitations of the traditional next sampling bandwidth. Since CS was first proposed in 2004, it has aroused widespread concern in the academic community, which is widely used in various fields such as information theory, wireless communication, and data processing. When data is sparse or compressible, can directly acquire a condensed representation with no or little information loss through linear dimensionality reduction, as shown in this picture. All the time, CS mainly have 3 research directions: sparse representation of singles, the design of measurement matrices, and the recovery algorithm such as OMP. The sparse representation of the single is the premise of the CS framework. Moreover, measurement matrix plays a dual role in the process of CS, which not only ensures that we can capture and preserve valuable original information of the single with fewer measurements possibly, but also influences the performance of the recovery. Finally, it is also important to design an effective and fast algorithm to recover the single. Although these 3 issues are related, it is generally recognized that designing a stable measurement matrix is helpful for several other aspects. So, we need to pay attention to the construction of a stable measurement matrix. Nowadays, measurement matrices are mainly divided into 2 types. The first type is random measurement matrices, such as random Gaussian matrix, random Bernoulli matrix, particle Hadamard binary matrix, and particle Fourier matrix, which can satisfy RAP with great probability. However, random matrices have the disadvantages of uncertainty and waste of storage resources, which limit their practical applications. For example, the storage space required for random Gaussian matrix elements is large, and its unstructured nature leads to complicated calculations. The second is deterministic measurement matrices, which can overcome these shortcomings. Commonly, there are TOPSIS matrix, circular circular length matrix. However, the construction of the deterministic measurement matrices is hard and is difficult to handle large singles. The RIP simplifies the investigation of CS reconstruction and provides the best guarantee currently known. Well, it is very difficult to judge whether a measurement matrix satisfies RIP. In order to reduce the complexity of the problem, it is another key point to find an alternative method that can easily implement the RIP condition. Also, if the measurement matrix and sparse spaces are guaranteed to be irrelevant, the measurement matrix satisfies RIP condition with a high probability. In this paper, it is found that starting from the low bound of correlation, some series have proved that the performance of measurement matrix is better when the correlation bound is closer to Welch bound. In order to reduce the randomness of random matrix and simplify the construction of measurement matrix, this paper proposed a set of measurement matrices satisfying the optimal Welch bound. Moreover, theoretical verification and experimental analysis show that the measurement matrices proposed in this paper have good performance. Next, I will mainly introduce measurement matrices satisfying Welch bound constructed in this paper. The first matrix is based on Hadamard matrix and screened by Welch bound. The Hadamard-Welch matrix (HWKM). The concrete steps to realize are as follows. Step 1. We select a size of n times n Hadamard matrix and randomly select m rows from it to generate a particle Hadamard matrix. Then replace the -1 value in the matrix with 0 to generate a 0-1 matrix, and unit the Coulomb vector to obtain the matrix size of m times n. Then determine whether its correlation satisfies Welch bound for screen. If the correlation is satisfied, the matrix is required to be output. Otherwise, step 2 is performed. Step 2. If the value of m or n is too large, we may not find the matrix that satisfies the Welch bound condition. In this case, we can get the basis matrix by canonical decomposition for the matrix of known size m times n. The basis matrix S that satisfies Welch bound is smaller and easier to find. Then step 3. If the matrix S satisfies the Welch bound condition and its Coulomb vectors are unitized through mathematical verification, the matrix expanded by canonical product of matrix S also satisfies the Welch bound, which is measurement Hadamard-Welch matrix HWKM. We seek. At the same time, due to the characteristics of the family of low correlation sequences, The matrix HWKM that meets the Welch bound has been verified to meet the low correlation requirement of measurement matrix. The matrix Hadamard-Welch circulant matrix HWCM constructed by cycle shift has also been verified to meet the low correlation requirement of the measurement matrix. Next is mainly my theory proving department. Assume the basis matrix satisfies the Welch bound and its column vectors have been unitized. The matrix expanded by the canonical product can be proved also satisfying Welch bound. The key point is to prove Formula 3. Here are mainly use mathematical induction. Here is the proof of the second matrix. By cycle shift, construct a measurement matrix from a circuit site. In the third part, performance analysis, the RIP of matrices are represented by the form of images. The random Gaussian matrix, particle Hadamard matrix, and measurement matrix HWKM and HWCM constructed in this paper. We can clearly find that the measurement matrices HWKM and HWCM have similar properties with random Gaussian matrix and particle Hadamard matrix. From the last two subgraphs of each row, we can find that the diagonal entries of the grammar matrix converge to 1, and the non-diagonal entries float around 0. Which means that the measurement matrices HWKM and HWCM satisfy the RIP. Then we compare traditional random Gaussian matrix, particle Hadamard matrix, and measurement matrix HWKM, HWCM constructed in this paper, and analyze the results both in noiseless and noisy environments. As seen in this picture, in noiseless environment, when the sparsity k less than 40, the measurement matrices HWKM, HWCM constructed in this paper have smaller recovery error, higher signal to noisy radio, shorter recovery times than random Gaussian matrix and particle Hadamard matrix. Also, in noisy environment, when the sparsity k less than 40, the measurement matrices HWKM, HWCM constructed in this paper have smaller recovery error, higher signal to noisy radio, shorter recovery time. Pink and blue. Through the above simulation, it is found that the measurement matrices HWKM and HWCM constructed in this paper have better reconstruction of performance than the random Gaussian matrix and particle Hadamard matrix in the appropriate sparsely rich under the same conditions, no matter whether it is noisy or noiseless. If you have any questions, you can contact me by email. That's all. Thank you for your attention.
My name is Wu Shuwen from Chongqing University of Posts and Telecommunications. The title of my paper is An Improved HMFCW Algorithm for Region in RFID System. We proposed an improved algorithm when the phase with large error exists. My presentation is divided into 5 parts: the introduction, brief review, introduction for improved HMFCW algorithm, and the simulation and the experimental results. The last part is conclusion. Let's start with the introduction of positioning technology. The positioning system built in this article is based in RFID. In RFID positioning technology, there are methods based on TOA, RSS, POA, for instance. The current phase-based RFID region system can be divided into 2 kinds according to the scene. The one is tag or radar in the system move, and another is stationary. In recent years, Yunfei in Cornell proposed a method to expand the bandwidth of RFID system, which created favorable conditions for solving ambiguity, and he proposed the HMFCW algorithm. Nevertheless, when the error of phase at some frequencies is large, the region accuracy will decrease. In order to solve this problem, this paper conducts a more in-depth study on the basis of it and propose improved HMFCW algorithm. RFID system proposed by this paper is shown in this picture. The computer is the control center, and the system consists of 2 kinds of transmitters and the receiver. Transmitter 1 is a radar, transmits a high-power frequency signal to activate the tag, and the transmitter 2 and the receiver are USRP devices to locate a tag. One USRP transmits a low-power signal by frequency hopping. Other USRP receives the data returned from the tag, and the data is used for region. Radial waves propagate periodically. The phase will change to pi when the wave propagates for a distance of 1 wavelength in space. It can be seen that the true change of phase caused by the distance d is theta is 2 pi multiply f and t. Due to the periodicity of signal, the phase measured by the receiver is not the true phase, but a wrapped phase. The relationship is true phase is wrapped phase plus 2n times pi, while n is the integral of cycle. The phase is from negative pi to pi. Combined phase is of different frequencies. The relationship between phase and distance can be expressed as following. In the equation, n and d are unknown, phi and lambda are known, but only non-negative integers can be used in n, and the range of d is also limited. so the N and D can be solved. The method of solving phase distance equations is shown in figure. Assuming that the radar obtains the phase is at 4 different frequencies. Get the distance and add 0, 1, 2 tier n times wavelengths to get multiply distance. There is a value very close to the actual distance, and the maximum cycle number is determined by the region range. HMFCW algorithm provides the same error tolerance for the observed phase at different frequencies. The serial and steps of HMFCW algorithm will be introduced in detail below. HMFCW algorithm proof by contradiction. Since the gap between the distance of the adjacent cycle number is smallest except the correct number, the unique solution can be guaranteed when the adjacent cycle number fails to pass the judgment. So we can get the judgment is pi multiply the difference between Fmax and Fmin, then divided by the sum of Fmax and Mmin, where Fmax is the maximum frequency of frequency hopping signals, and Fmin is the minimal frequency. The value is most reasonable because it obtains the maximum value under the condition that the cycle number is correct, and the value is called the error tolerance. We substitute variables into judgment. If we can get a cycle number, then we can obtain the region result. If no cycle number passes, then the error tolerance will be enlarged by 1.02 times and return to judge. But in the actual process of getting phase, the error of phase at certain frequencies may be too large, which is called the point with large phase error. If the point with large phase error is substituted into HMFCW algorithm, it may cause large error. In order to explain the impact of it better, the situation before and after adding the point with large phase error is shown by finger. The phase error is taking 0.8 radians and negative 1.2 radians on 900 MHz and 930 MHz. In Figure A, only the first class of clustering results has no mark, indicate its result is past the judgment. The result of region is consistent with the true distance. In Figure B, the clustering results of the true distance, the first class cannot pass the judgment at least 2 frequencies, while the adjacent clustering results the third class passed. So the final result is 1 wavelength smaller than the true distance. The region error becomes larger. Therefore, it is necessary to possess the points with large phase error. To solve these problems, this paper proposes an improved algorithm based on the phase error tolerance method. We will set an initial value for the critical value of error tolerance at the beginning. If the error tolerance exceeds the certain critical value, the point with the largest phase error will be removed, and the remaining distances are judged. This process iterates until the clustering result passes the judgment. The algorithm calculates the ratio of the points with large phase error in the measured phase first generally, and then adjusts the critical value to ensure that the ratio of the flattered phase in the algorithm is close to this value. In order to test the region accuracy of this algorithm, a multi-path channel model is constructed. The phase at each frequency has a 15% possibility of being replaced with a pointer with a large phase error to simulate the actual receiving phase. The error of the pointer with large phase error is within 0.5 to 2 radians that obey uniform distribution. In the two cases that with or without points with large phase error, calculating the region error, it can be seen from the figure that when there is no pointer with large phase error, the improved algorithm and the HMFCW algorithm have similar region errors. The error of WBPDOA algorithm is larger than the other algorithms. When there are points with large phase error, the improved algorithm has a higher accuracy than HMFCW algorithm. The cumulation probability of improved HMFCW algorithm is 18.7% higher than HMFCW algorithm when the error of region is within the range of 0 to 3 cm, while the region error of WBPDOA algorithm is still larger than the other algorithms. We can see the improved HMFCW algorithm can be more effective to eliminate the influence of pointer with large phase error. The algorithm is verified by experiments, and the place of experiment is shown in the figure. All USRPs are close to wall. The heights of the tag and the receiver are seen. The yellow marks in the finger are test points. The interval between two adjacent points is 0.5 meter. 25 positions are tested. The height of the tag remains unchanged when the position of tag is changed. In the experiment, most difference of phase is within 0.3 radians, while at a few frequencies, the difference of phase exceeds 0.7 radians. Let's see, there are points with large phase error in the region measured phase. Region errors of each internal at the 25 positions are shown in figure. The region area of improved algorithm is concentrated in half of one with slice. This is because the region area is mainly determined by the cycle number. Improved algorithm lead to only the correct cycle numbers, and the adjacent cycle number can pass the judgment. When the error of HMFCW algorithm is about one wavelength, improved algorithm improves about half of the situation. When the consequence of HMFCW algorithm is correct, improved algorithm can also be correct. This paper proposes improved HMFCW algorithm to solve the problem of points with large phase error. We can enable high accuracy on region and localization. We believe the proposed approach can provide a new idea for RFID indoor localization technology. That's all my presentation. Thank you for listening.
Ladies and gentlemen, it's my honor and pleasure to present my paper, And the title is Efficient Unmanned Aerial Vehicles Assisted D2D Communication Networks. I am Winston Zhang, and we come from the Wireless Communication and Network Lab at NCKU. And this is the outline of my talk. We will first give a little bit introduction about the UAV Assisted Communications Network, and we will formulate our problem, and we propose our sequential UBS deployment algorithm. UBS means UAV base station, and we will present our simulation result and give our conclusions and suggestions for future works. Imagine that if we embedded base station onto the UAV, we can provide better channel and environment for mobile communication systems. This is not a fancy imagination. Nowadays, people are beginning to build the elevator to enter the space. So just embedded base station onto the UAV can be a practical application. There are a lot of related work about how to locate UAVs. We can apply the UAV to extend the coverage, and we can empower a UAV to have some energy harvest capability. In this case, we can use UAV to charge the cluster heads for a hyperdense sensor network, and such that the lifetime can be extended. And actually, this is one of our ongoing research topic. And we also can cluster for the ground terminals, because the ability of UAV is limited. It can just serve a limited number of ground terminals. So clustering helps us to serve more and more terminals on the ground. And with clustering, we need to reselection our cluster heads. And we can also apply the interference avoidance resource sharing scheme, such that the limited resources on the UAV can be fully utilized. For example, the spectrum, the limited spectrum, limited power, something like that. And we can apply the beamforming technology to provide better channel gain. And we can design the pre-coding and post-coding to improve the signal quality. And we can also design some power control algorithm to control the interference. And we can have better user association for the ground terminals and UAV. And we can also design the trajectory for UAV to route through different areas to provide, for example, packet delivering or messaging or information collection services. So we have a lot of related work about the energy harvest, clustering, user association scheduling, mobile edge computing, cache-added computing, multi-UAV trajectory, or just a single UAV trajectory. In my mind, we can apply UAV to help the small cell network on the ground. We can use UAV to improve, for example, the energy efficiency for the ground-based stations. And we can apply the multi-hub D2D transmission scheme to extend the coverage of a UAV, like these figures. And we can use one UAV and route through a lot of cluster heads, and clustering and the routing UAV help us to extend the network coverage. In reference 2, we see that the blue square here is the UAV, and we have one UAV control this 4 UAV, and we have this UAV to control this 2 UAV, and the whole UAV construct internet in the air, and the whole network can provide services through a UAV, and this UAV is near to the ground terminal. And in this work, they use the feather value we were introduced in the letter to describe the connectivity of the network in the air. And it has some SI requirement for all the link, but not include the D2D connection on the ground. And in this work, we try to build a 3D network. And for example, we have one base station here, but it has already out of function. And so we need to deploy UAV to serve different group of peoples. And we want to construct an internet in the air such that all the people can be connected. But we try to use the minimum number of UAV to provide UAV assisted D2D communications. And this true figure is to describe the line of sight and non-line of sight channel environment for the UAV. If the angle is large enough, like as shown in the figure, if the angle is large enough, we can provide a line of sight channel environment for the whole group of people. But if the angle is too small, it will become a non-line of sight environment. As shown in this figure, we want to use UAV to connect a 3D network. And imagine that this base station is out of function. So we need to deploy UAV to serve different group of people at different area. For example, in this figure, we use 3 UAV to serve 5 groups of people. And these 3 UAV are interconnected. So all the people in this area can connect with each other with the assistance of the UAV. And this true figure shows the line of sight and non-line of sight channel environment for the UAV assisted communication network. If the angle here is large enough, then this group of people can have a line of sight environment with the UAV. But if this angle is too small, like this one, it will become non-line of sight channel environment. And we can use this matrix to describe the interconnectivity of between UAVs. For example, the yellow edge here connect UAV 1 and UAV 2, and we will put 1 and 1 here. And the red edge connect UAV 1 and UAV 3, and we put 1 and 1 here. And so on, we can do the same thing for the blue edge, the green edge, and the pink edge, and we form this matrix. And we call it the Laplacian matrix. And we can use the second eigenvalue of the Laplacian matrix to describe the interconnectivity of the whole network. And we want to maintain this connectivity subject to all the SIR requirements in the whole 3D network. That means the interconnectivity between UAV need to satisfy the SI requirement, and all the ground terminals need to satisfy the SI requirement. For example, a member node need to have a good channel quality to transmit data to each cluster head. So we need to guarantee the minimal SIR requirement. And now the question is how and where we want locate our UAV. For example, if we want to serve this group of people, we will search the possible location within this square. And this square is formed by this group and the central controller here. This controller is to control the UAVs. We may call this the control station, something like that. And then we will find an area. And in this green area, UAV can serve this group of people and still connect to the control station. And if we want to use the same UAV to serve this group of people, and we will find the blue area here. But the blue area here is too far away from this group of people, so we need another UAV to connect this group of people. So we call it the sequential UAV deployment algorithm. So we do it sequentially such that we can find a better intersection area, and in that area we can deploy a UAV to serve all the people on the ground. And this is our simulation parameters. And these two results is to show the probability versus the number of hubs for different SI requirements. For example, if we increase the SI requirement from 40 dB to 50 dB, that means the distance between hubs, between two, the distance for one hub needs to be shorter, such that we can have a better link quality. If the hub distance is too large, we cannot satisfy the SI requirement. So if we have a higher SI requirement, we need to build the more hubs. So this figure can obviously show that we need more hub compared to this case, and compare between our propulsion scheme and the conventional scheme in reference 7, we can see that we will build more hubs. With this two figure, we can find that our proposed scheme needs less hub to build the whole network, because we can use small number, we can use less UAVs to build the whole network compared to the conventional scheme in reference 7. And this two figures want to show that if we want to build a high spectrum efficiency network, maybe we will lose some interconnectivity. For example, like this figure, at the SNR about 45 dB, we can reach the highest spectrum efficiency, but at the same SNR requirements, the factor value is lower, or is the lowest. That means the high interconnectivity does not guarantee a high spectrum efficiency. And I think this is the most important discovery of our paper. So this reminds us that if we want to build a high spectrum efficiency 3D network, we cannot just judge it by the feather value. Feather value is not the most important figure. And also, if we increase the SR requirement, we need more hubs. Just as what we mentioned for this two figure. And so we need more UAV, like this curve shows. And in this work, we have developed a scalable UBS deployment algorithm to construct an UAV-assisted D2D communication network, and we can achieve a higher spectrum efficiency. Although the interconnectivity cannot reach the highest point, but what we want to put emphasis is the spectrum efficiency is the most important things for the whole 3D network. And we have a lot of future works for the study. For example, we can design a trajectory. We can design some power control algorithm to improve the spectrum efficiency or to eliminate the impact of interference. And we can consider the mobile edge computing, also the computation capability distribution. So we need to distribute the computing bits, computing capacity, or we can take the schedule into account if we are doing the hyperdense network, and we might build some routing algorithm for some complicated network structure. Thank you. And this is our reference.
Good morning, ladies and gentlemen. This is my honor to have the opportunity to be here to give my presentation. My name is Li Zhang, and I come from Southeast University. My title is Early Stopping for Noisy Gradient Descent Bit Flipping Decoding of LDPC Codes. The outline of this speech is divided into 5 parts. They are background, problem formulation, an early stopping criterion for multi-bit noisy gradient descent bit flipping decoding, simulation results, and conclusion, respectively. First, let me introduce the background. The soft decision algorithms have an excellent BER performance, but this comes at the cost of high computation complexity. The iterative soft decision decoder will not stop until a valid code word is found by parity checking, or the perceived maximum number of iterations is reached. In many cases, the maximum number of iterations exceed 100 for better BER performance. However, what often happens at low SNRs is the valid code word cannot be found. Under these scenarios, the soft decision algorithms will continue to run until the maximum number of iterations is exceeded, and therefore a lot of energy and time are wasted, especially when the maximum number of iterations is large. Therefore, how to detect and stop the decoding of undecodable blocks at an early stage is worth studying. For soft decision algorithms, an early stopping criterion is based on the convergence of mean magnitude of the log likelihood ratio messages at the output of each decoding iteration. Another early stopping criterion is based on the variations of the number of satisfied parity check constraints. So, how to design an early stopping for the MNGDBF algorithm with a fixed threshold? We believe it is important that the early stopping criterion for the BF decoding algorithms should be much simpler than that for the BP decoding algorithms. Given the lower complexity of BF decoding algorithms compared to the BP decoding algorithms. Next is problem formulation. As we all know, the NGDBF algorithms have an objective function and an inversion function. The code word to solve the maximum likelihood problem is also the solution to maximize the objective function. The GDBF algorithms are shown by regarding the ML problem as the gradient descent optimization problem of an objective function. The optimal value of the parameters of the NGDBF algorithms are relative to the value of SNR. But in absence of an external SNR estimator, the variance of the QK can no longer depend on SNR. Thus, we set all the parameters to be constant. Now, let me introduce the multi-bit noisy gradient descent bit flipping algorithm. The first step is initialization. T is used to record the number of iterations. The second step is to compute the bipolar region and verify whether it is a legal codeword. If it is a legal codeword, output X and stop. Otherwise, add the value of T. The third step is to calculate the inversion function at each bit. In the fourth step, all the bits whose inversion function is lower than the inversion threshold will be flipped. In the last step, if the number of iterations do not reach the maximum number of iterations, repeat steps 2 to 4 till a valid codeword is detected. Otherwise, output X and exit. Figure 1 illustrates the average number of flipped bits for success and failure of MNGDBF decoding at different iterations and SNRs. As can be seen, the average number of flipped bits in the failure cases of NGDBF decoding falls more slowly as the number of iterations increases and remains at a higher value than that of the successful decoding cases, especially during the first 20 iterations. For example, the average number of flipped bits in the decoding failure cases at 2 dB hardly drops, and almost all of them exceed 140 throughout the iterations. Based on this observation, we use the number of flipped bits at certain iterations to predict and decide whether to stop the decoder. The algorithm with early stopping starts out the same way as the MNGDBF algorithm, and in step 5, the early stopping criterion is being checked. Let S denote the set of iterations in which we will check the number of flipped bits. If the current iteration is in S, we record the number of flipped bits in this iteration and check this number against a predefined threshold lambda. If the number of flipped bits exceeds lambda, we deem that this block will not be decoded successfully, and we stop the algorithm. Otherwise, the algorithm proceeds normally, as in the MNGDBF algorithm. Hence, S and lambda are two parameters of the proposed algorithm, and their values shall be obtained empirically through simulation. Next is simulation results. Simulation results are based on PEG 504 plus 1008 regular LDPC code from McCase's online encyclopedia on the AWGN channel with BPSK modulation. Figure 2 presents the BER, PLER for the MNGDBF and ESMNGDBF algorithms. The ESMNGDBF algorithm with S equals 1, 10, 20, and lambda equals 140 has almost the same BER and PLER performance as the MNGDBF algorithm at low to middle SNRs, and a little performance degradation at high SNRs. Since the complexity of the proposed early stopping criterion is extremely low, and it is designed for the BF algorithm, a certain BER and BLER performance degradation at high SNRs is acceptable. Figure 3 presents the ANI for the MNG-DPF and ESMNG-DPF algorithms. ANI represents the average number of iterations. Note that the ANI of ESMNG-DPF with S equals 1, 10, 20 and lambda equals 140 drops to about 30%, 50%, and 80% of the ANI or MNG-DPF at 2 dB, 2.5 dB, and 3 dB respectively. The ESMNG-DPF algorithm is sensitive to the precise variance of the threshold lambda. The value of the threshold lambda is found empirically through a numerical search. This search may produce different values for different codes and algorithms. Some examples are shown in Figure 4 and 5. According to Figure 4, with the same set as the ESMNG-DPF with lambda equals 140 has less BER and BLER performance loss than that with lambda equals 130. But the decline in ANI is also smaller, as shown in Figure 5. As with the value of threshold lambda, the set S is found through an empirical search. Figures 6 and 7 represent the result of an example with parameter lambda equals 140. When the number of elements in the set S increases, the value of ANI at low SNRs becomes smaller, and the BER performance loss at high SNRs become bigger. It is shown in the Figure 7 that the decreases in ANI at low SNRs is relatively large when the number of the elements in the S increases from 1 to 2 and from 2 to 3. When it is further increased, the ANI at low SNRs hardly decreases. Obviously, there is a trade-off between the number of elements in the set S and the ANI at low SNRs. Since the BER and BLER performance degradation should not be too large, it is best to set the number of elements in the set S to 3 in the ESMNG-DPF. The value of the 3 elements in the set S are obtained through simulation. Now, I am about to conclude my presentation with an extremely small amount of complexity increase. The proposed early stopping criterion can significantly reduce the number of decoding iterations at low SNRs, while the BER and BLER performance at high SNRs is slightly decreased. That's the end of my presentation. Thank you very much for your listening. If you have any questions, please do not hesitate to ask me.
everyone, my name is Yumin. The title of this video is Polite Allocation Based on Match Learning Algorithm and User's Angle of Arrival in Massive MIMO System. As we know, 5th generation has arrived. 5th generation is a new generation of mobile communication system for 2020 with high sequential efficiency and low power consumption. In terms of transfer rate and resource utilization improvement over 4th generation system 10 times. Its wireless coverage performance and user experience will be significantly improved. 5th generation will be closely integrated with other wireless mobile communication technology, constitutes a new generation of ubiquitous mobile information network to meet future mobile internet traffic 1000x development needs in 10 years. The three main applications of 5th generation are UILC, MMTC, and EMBB. First, with diversity, second, our transmit performance demands different. 5th generation cannot have solutions for all sectors. In addition, the current wireless technology innovation has a diversified development trend. In addition to the new multi-access technology, 5th generation can play a key role in the major technology sector. And one of the key technologies of 5th generation is massive MIMO. Massive MIMO system is one of the key technologies of 5th generation mobile communication systems. It is configured a large number of antennas on the base station side. The system capacity can be greatly increased. It brings high energy efficiency and high supreme efficiency. Massive MIMO technology has attracted much attention because of those advantages. One of the problems in massive MIMO systems is polite pollution. Due to the number of antennas, the number of original polyps is limited by channel covering time. It leaves a limited number of original polyps. The polyp sequence is reused by neighboring cells. The interface caused by non-original polyp sequence is called polyp pollution. Polyp pollution greatly limits the system performance. Therefore, it is particularly important to study how to reduce the impact of polyp pollution. We propose the polite allocation based on machine learning algorithm and users' angle of arrival in massive MIMO system. Firstly, different from the previous way, we propose to group the users multiple times. Firstly, group according to whether the users' angles of arrival overlapped with each other. Users were divided into NGI categories. The first N categories respected users whose angle of arrival did not overlap, and the others respected users whose angles of arrival partly and overlapped or completely overlapped. We proposed the K-means clustering algorithm to divide the NGI categories users. Because of the large number of users in MIMO system, we use an unsupervised machine learning algorithm, which is suitable for massive data processing. K means clustering algorithm to group the NGA users into two groups according to the interference cost. The function measured the amount of interference between users. It divided users with high interference into interfering group, and the user with low interference into non-interfering group. Finally, performed different policy allocation schemes for users in different groups. And we set the cost function. The target, the user gradient vector of the piece path is alpha theta AP. The interfering user's gradient vector of piece path is alpha theta BP. We define the interfering cost function as JAB. When the number of antennas port on the base station side was large enough. Yeah, we can see that. When the interfering user's angle of arrival and target user angle of arrival partially overlapped or completely overlapped, the amount of interference from the interfering users to the target users will inversely proportional to its relative distance. We can assume that cosine theta IP equal cosine theta JP equal 1. The simulation results were as shown in the figure 2. It can be seen from the figure that when D equal 1000 and J equal 0.0002, the amount of interference between users is almost negligible. Based on the above results, for set NGI users, is fair to use the unsupervised machine learning algorithm K-means clustering algorithm to classify user according to the user's location information. The users were further divided into K clusters. Those clusters with a distance between cluster centers greater than 1000 were divided into non-interfering group, and those clusters with a distance between cluster centers less than 1000 were divided into interfering groups. And the K-means clustering group shown in table 1. Initial input. K is the number of clusters. Usually is a minimum value used to determine when the clustering ends. CNGI is the user location information who's near the cluster. And the second step is parameter initialization. And the three steps is calculate the distance of each user relative to the cluster center. Fourth step is attributing the user with the smallest distance to clusters. Update clusters center and calculate decision parameters. And the three part is polite allocation. Polite sequence were randomly allocated to the first n types users, and each group of polite sequence was multiplied in each user set. The user in the interflowing group were accepted strictly original polite sequence, and the users in the non-interfering group were randomly assigned polite sequence. And the analysis of simulation results show the three features. The first one is the location of user in the cell in the system. The feature 2 is polity, the efficiency of different polity location algorithms with different numbers of antennas. And the three feature is users minimal upstream reachable rate with different numbers of antennas. And the scheme includes user arrival angle group, k-means clusters grouping, and polite allocation. On the one hand, the polite allocation scheme based on machine learning algorithm and the user angle of arrival proposed in this video can efficiently suppress the impact of polite pollution on the performance of massive MIMO system and efficiently improve system performance compared with random polite allocation schemes. On the other hand, compared with political location scheme based on user arrival angle, the polite allocation scheme based on machine learning algorithm and user angle of arrival posted in this video can effectively improve the polite efficiency and reduce the polite overhead. It's suitable for massive MIMO system. More. Okay, thank you.
My name is Yang. My topic is a method of node importance measurement based on community structure in heterogeneous combat networks. First of all, I will introduce some background. At present, the research on the importance of complex network nodes in the military field is still in the preliminary stage. Offcell analyzed the key node identification method based on the node centrality. Martin proposed that the node between it can reflect the dynamic characteristic of the network. Freeman improved the important node identification method based on betweenness. And Lewis proposed a method take the approximate flow betweenness of node as an indicator for centrality measure, which improved the algorithm complexity. Most of above mentioned improvements are designed for calculating betweenness centrality, but HCN is a typical open complex giant system, which is composed of many community structures with different sizes. Combat network must indicate following 4 characteristics. First, command and control relationship between superior and superior, such as this is a high level node, is a lower level node. Each represents the communication. And the second, collaboration within the community, such as this kind of link. Third, the collaboration between communities. And fourth, inter-level command relationship. So we use 3 diagrams to represent previous 2 characteristics of combat network. And to indicate characteristic 3 and 4, we can add age. For example, from this node to this node, these 2 nodes are in a different community. In any military operation requires the cooperation of different forces. This is because the capability of single network unit is very limited. And in order to maximize combat capability, we need to combine multiple functional combat units. So we apply operation loop. According to the timing of combat missions, we divided the nodes into 3 parts. First is the sensor entities, such as equipment that execute early warning or detection, and decider entities. For example, equipment that executes commanding and controlling assignment, and influential entities, such as equipment that executes striking, such as tanks or fighters. A complex combat operation is as follows. Once sensor node S found the target, it will transmit the target information to the decider node, such as operational center. And then the operational center, node D, comprehensively analyzes the received information and then issues instruction to the influencer, that node I, to execute military operation on the target. And finally, the offensive and defensive engagement node, I, attack the target. So they form a simple loop. And in addition, decision maker node D will adjust the sensor S according to the changing combat environment. That is the age D to S. And the sensor S will also redetect the combat situation after the node I conduct military operation on the target T. So that is the age I to S. And the function module has 4 age. The combat space is divided into different communities. Each community can be expanded based on the operation loop that is a functional module. So there is a simple compact network. Different color represent different community. And node 24, 22, and 23 compose the function module, and the yellow community consists of 4 FM, like this one, this one, this one, and this one. So that's a compact network we use. And in third part is my importance measurement to evaluate the importance of nodes based on the community structure. We must first accurately identify the community structure of the network. Here we benefit from the high-order clustering of complex network to define a module conduction rater. HCN is depend on a function module to complete a military operation. So the community detection of the combat network should take functional module as a combined unit. After the detection, the number of function modules in each community is roughly the same, and the function modules are destroyed as little as possible. So our algorithm has two goals for founding community in the network. There should be as many nodes as possible in the function module of each community, and the number of the broken FM should be as few as possible. These two conditions can be reflected through the erosion cut. For example, once division community, such as this dotted line, will make this FM broken. So the WM is the number of broken FM, which at least one node in FM in SI and another node in another community. Also, vol M is number of nodes belonging to function module M in SI, this community. As the number of nodes increase, it is an NP problem to accurately calculate the minimum module conduction rate. So we propose an optimization algorithm to obtain an approximate optical solution. A spectral graphic closing algorithm based on eigenvector. The algorithm is high calculation efficiency and easy to implement. Also has approximated optimal mathematic guarantee for the obtained clustering. The approach consists of such two algorithms. For the beginning, we enter known network model and the functional module to form the module adjacency matrix. The element in the matrix is the number of modules that contain both node I and j, and then calculation module weight matrix by calculate the diagonal matrix of the module adjacency matrix, and then calculate the Laplacian transform of the module weight matrix. In step 4, we can calculate the eigenvectors corresponding to the k-smallest non-zero eigenvalue of the Laplace transformation matrix, and then arrange the eigenvectors into the matrix of n times k and normalize the matrix. Each row vector represented a node, and then use the sub-algorithm to group the nodes. Sub-algorithm is an improvement of the k-means algorithm, including the following steps. First, select the initial community center node according to high centrality and discrete distribution. Node has higher centrality and more decreted distribution is more likely an initial community central node. In order to measure the depression of nodes, we calculate the minimal value of the distance between a node and other nodes with higher centrality by using the minimi distance. The Euclidean distance between the representative vector of node I and j in the vector y is this dij. The node has the largest centrality. It is more likely to be selected as the initial central node. So we take the minimum distance as delta k, or it's a maximal delta I. Step 2, we divided the node into the community to which the nearest central node belongs by calculating the distance between the node and each central node. Then calculate the MCR at this time. Then we calculate the average shortest path from nodes in each community to other nodes in the community, and update the central node of the community with which has the smallest average shortest path. And repeat step 2 and 3 if the central node no longer change or the number of iterations reach the upper limit. We will stop the algorithm, and the division result with the smallest module conduction register is the approximate optimal solution. Then we define the value for each node. Is this IEBC importance evaluation based on community to indicate the importance of the node. C is the aggregate number of communities in HCN. SW is the number of nodes in community W. And VIC is the number of community connect to the node I. Then we calculate the value of IEBC of each node and obtain the important node by sorting this value. The sort algorithm is as follows. First, we enter the network module adjacency metric and detect communities by approach proposed in previous community division, and then compute the number of community connected to the node I. Step 3, we can generate the list of IEBC of each node counted by the formula previously proposed. At last, sort each node by the value of IEBC. In first part is my simulation and analyze. There are 6 kinds of link in a combat network. Each link has different connection probability in actual military operation. The ratio of the actual number of links to the number of possible links between 2 nodes, where n d2s is the actual number of link for node D to node S. In this paper, associated with corresponding military application, we use 300 S node, 150 D nodes, and 550 I node are randomly generated. And the given connection probability is as follows. In the picture, red represents node D, blue represents node S, and gray is node I. Then apply several importance ranking methods, such as degree centrality, between centrality, closest centrality, and eigenvector centrality, and our method of IEBC to rank the node importance. Here are top 12 most important nodes arranged by different methods. According to the importance of ranking result, we attack the node of HCN. As the node is damaged, some nodes connected with it cannot communicate each other, so it's causing the entire HCN to split into many independent connected giant components. We use the number of nodes in maximum connector component and the number of surviving functional modules to evaluate the function response of damage HCN. Here are my simulation result. You can see in the figure the trend of edge is sharply reduced and then gradually flattened. And attacking node with the IEBC measurement result, the decreasing speed of edge is the fastest. We can see that. So the important node detected by IEBC are the nodes with the most link. This node maximizes the spread of information in the community. When such nodes are detected, the community will separate. And this is the number of surviving FM virus with attack intensity. As the attack intensity increased, the number of surviving FM decreased. It's shown that the nodes detected by IEBC are more important than nodes identified by degree century or other centrality method. And the node detected by IEBC are more likely a D node because surviving FM decline the fastest as the D node under attack. When all D nodes are damaged, the node of FM reduced to 0. Thanks. That's all.
Hello everyone, my name is Jiang Han, come from Chongqing University of Posts and Telecommunications. My topic is research of timing, synchronization, algorithms of cell search in the fifth generation wireless systems. At first, I will introduce the outline of my paper. The outline, including introduction, PSS screens, intercoloration, agreement, precise coloration agreement, explainer result, and conclusion. Introduction. The fifth generation new reader is the fifth generation mobile communications technologies standard developed by the third generation PASS chip project organization. Since 2019 years, many countries and regions around the world has launched the fifth generation wireless systems service and fifth generation wireless systems and has become the mainstream mobile communication standard. The first step of cell search is to realize the detection and inspection of primary synchronization singular. The accuracy of detection directly affects the establishment of communication links, and the fifth generation wireless systems have more stringent requirements for frequency of set. Therefore, the study of timing synchronization arrangements, which high precision and low complexity, is of utmost importance. PSS screens the number of physical cell IDs in the fifth generation NR system increased from 504 to 1,008 and was divided into 336 groups of 3, each is different for LTE. In the formula belong to for 0 to 335 is called the cell group ID, and the formula belong to 0, 1, 2 is called the intracell group ID. Intercorrelation agreement. PSS has had a good cross-correlation property that can achieve timing synchronization by receive single directly correlate, which locked PSS single. After detect the reliable peaks, the vector function is with disadvantages. 1. High computational complexities. 2. Poor frequency offset resistance. Piecewise correlation agreement. However, in practical application, there are inevitable problems such as carrier deviation. Their traditional cross-correlation agreement can not effectively slow the frequency deviation. Piecewise correlation synchronization agreement has had good frequency deviation resistance ability in the case of language frequency deviation, the manufacturer factions. With disadvantage of high computational complexity. To solve these problems, I come up with proposed agreement. First, 3 sets of locked screens will accumulate into a set. The optimization in formula for becomes as shown in the future, the correlation of the accumulator screens is consistent with the peak part of traditional cost correlation. Assuming that there is just frequency deviation in channel and other conduction, I perfect the family of reserve single is. Second, the different cost correlation of the reserve single and the sum proposed locked PSS single is operate with the flow expression. The different cost correlation argument can eliminate perhaps and reduce the influence of frequency opposite. In the 5th generation NR system, phi cross correlation is necessary to open a set of phi maximum peaks and determine the corresponding mu value and cross singulation port of the maximum. Mu belong 0, 1, 2, 3, 5 last. The important arrangement cannot get the NID2 in CR group direct, so I need get the ID through 3 groups of precise civilization. The experimental results show finger 2 show the correlation peak plot of the correlational cross correlation argument at delta equal to 0.2 and delta equal to 1.2 respectively. And figure 3 show the correlation peaks plots of the improved argument of this paper at delta equal to 1.2. It can be seen figure 2 that the transition argument has better detection performance at a small frequency region with obvious peak but a large frequency region. The peak is not obvious and the performance is poor, but a comparison between figure 2 and 3 show that the improved argument still has obvious peak and large frequency region. Figure 4 shows the cross-correlation between Q port length of the receive single and 3 groups of language singles to detect the maximum value of 3 groups of related states. Big phi represents the probability of detection between the improved and interrelative arrangements when equal to 0 and 1.2. It can be seen from the figure that the performance of the improved arguments in this paper is better than that of cost correlation argument, regardless of equal to 0 or 1.2. When the signal-to-loss ratio is constant, the detection probability decreased with the increase of factor deviation, and when the factor deviation is constant, the detection probability increased with the increase of signal-to-loss ratio. Concluding, in this work, by comparing and analyzing the improved agreement with the transition cross correlation agreement and segmentation agreement, the results show that the improved agreement has the best anti-frequency offset performance and lower computational complexity. On the other hand, improvement arguments proved a good trade-off in terms of performance and complexity. Okay, that's all. Thank you.
It is a great pleasure to work with such an excellent organizing committee team for their hard work in organizing and supporting the conference. We strongly believe that Chinacom conference provides a good forum for all researcher, developers and practitioners to discuss all science and technology aspects that are relevant to collaborative computing. We also expect that the future conference will be as successful and stimulating. Thanks Professor Chai Jun Zone's keynote titled Intelligent Reflecting Surfaces Assisted Wireless Communications. Thanks Professor Fei Goal's keynote titled Deep Learning for Physical Layer Communications, an attempt towards 6G.